I'm here with Julie. We're going to be talking about atmospheric rivers and especially the kind of how it's not only hazardous, not only leads to flooding, but it can also actually be beneficial, especially for the state of California, which has lots of drought. So I guess I'll just start off. Would you want to just do a quick intro of who you are and where you're doing research?
Yeah, so my name is Julie Kalansky. I'm Deputy Director at the Center for Western Weather and Water Extremes. So we are a center at Scripps Institution of Oceanography, which is part of UC San Diego. And we study atmospheric rivers, and we work on modeling and forecasting them and integrating the science into those forecasts to help improve those forecasts of atmospheric rivers.
Nice. And yeah, you mentioned the center that you work for, the CW3, and I just got to say, your guys' website is amazing. I'm going to be using that throughout this entire winter for all your different forecasts that you guys do. But I guess the first question would just be, what is an atmospheric river?
So an atmospheric river is just what it sounds like. It's really a river in the sky, but instead of running water, it's water vapor. And so there's these elongated plumes of water vapor in the atmosphere. And when it interacts with the mountains or other topography, or sometimes even dynamics in the atmosphere and lifts up, we can produce large amounts of precipitation, which is both rain and snowfall.
Yeah, that rain shadow effect's definitely something that we noticed on the Central Coast this last winter, where atmospheric river bumps up into the mountains, water vapor rises up, turns into clouds, get a ton of rainfall, and then drier conditions on the other side of the mountains.
Totally.
So it makes sense that most of the rain would be mostly in your mountainous areas, right?
Right.
No.
So if you look at just in general California, if you look at a map of California topography and California precipitation, the areas of higher elevations is generally where you get more precipitation. But atmospheric rivers do bring, rainfall and snow in some places at lower elevations.
Yeah, that was one interesting thing I was learning about recently is that atmospheric rivers can bring in warmer air, so it will actually lead to higher snow levels. Am I understanding that right?
Yeah, exactly. So generally, atmospheric rivers are a bit warmer than other types of storms. Of course, there are a lot of caveats, and this isn't always the case. But if you were looking at kind of a long-term climatology, they are a bit warmer than storms, and so snow levels are a bit higher typically with atmospheric rivers.
Gotcha. And is that kind of where the term Pineapple Express comes from because it's coming like from the tropics?
So Pineapple Express, I don't know the original, who originally termed the phrase, but oftentimes the direction from, the tropics around Hawaii towards California, that orientation can produce a lot of precipitation kind of central northern California. And so one of the things we know is the direction of the atmospheric river has a lot of impacts on where and how productive it is in producing precipitation or that rainfall. And those atmospheric rivers, Pineapple Express, are oftentimes some of the more impactful ones because of the orientation of the storm.
Gotcha. So it's almost like the really warm tropical water has a lot of evaporation. So you end up getting a lot of water vapor in the atmosphere. And then is it the jet stream that's funneling all that water vapor towards us? Or is it something else that's going on?
So not all, but many atmospheric rivers are associated with low pressure systems. And so if you can imagine a low pressure system, just kind of spinning. And as it spins, it pulls along this moisture and with those winds, forming the atmospheric rivers. They can form in other ways. And sometimes we'll see an atmospheric river without a low pressure system, but oftentimes that is how they form.
And would it typically be a rule of thumb that the stronger the low is, probably the faster your circulation is going to be around it, so then the stronger the atmospheric river would be?
Not not always. I mean, we saw in October of 2021 where there was this really strong atmospheric river that made landfall. It was an AR5, and that was associated with what some people are calling a bomb cyclone. So are those instances. I don't know if we can say like it's always a case because it also depends, how far away the low is, right? There's all these different situations or scenarios that can impact the strength of the atmospheric river and also, the low and how they interact.
Yeah, that's definitely one of the things I've noticed about the atmosphere is it's a lot more complex than maybe some people would hope. Like I was just doing a bunch of research into El Nino about does it lead to more rainfall in California and found out that the correlation is not nearly as strong as I was thinking it was. There's lots of variation in there.
Right.
That kind of ties into the next question though about how it's not maybe just simple like atmospheric rivers lead to flooding. Could you talk about maybe some of the different impacts that we see and whether it's like always bad or always good?
So atmospheric rivers can be both beneficial and hazardous. And actually at the center, our director with folks from National Weather Service and um, other partners have developed a scale for atmospheric rivers that range from, we call them an AR for atmospheric river 1 through 5. And ones or twos are generally beneficial, where threes could kind of go either way between hazardous or beneficial, and fours and fives are more hazardous. California gets about half its precipitation from atmospheric rivers. And so a lot of those are not ones that aren't necessarily super strong or super long in duration and can bring, good rainfall that we need for streams, landscapes, environment, reservoirs, all of those things. And so a lot of them are very beneficial. It's when you get atmospheric rivers that are extremely strong in strength and also that have longer durations, they kind of just hang out over a specific place where they're rather large, that they can produce, large amounts of precipitation, which can lead to flooding.
Interesting. So it's almost like it's very necessary in terms of water supply for California, but there's always the danger that you pick up too much rain too fast, and then that's where it leads to flooding out there.
Correct. And one of the things that we saw last winter, it wasn't any one individual atmospheric river, it was the sequence of atmospheric rivers that they came so close together. And the landscape is already wet and saturated, and so additional rainfall, it didn't, when it seeped into soils, and streams were already expanded. And so that sequence, or what we call a family of atmospheric rivers, can be very impactful too.
Yeah, I saw that great map that your center puts together that showed the different arrows going in.
Yeah.
And in the webinar that I watched that you guys put together, it was saying that Central Coast down to Southern California usually has 1.5 strong atmospheric rivers. And then last year we had 3 or 4 just bullseyes right on the Central
Right.
Coast. So it's almost like the soil gets saturated and then there's nowhere for that water to be absorbed into the soil. It's almost like a wet sponge. So then it just turns into runoff and flooding.
Exactly.
Gotcha. And then you mentioned the scale. I think that's one of the other really cool things you guys are doing at the center. Um, would you say, so you kind of already summarized this, but it's basically 1 to 2 you would say would be the mostly beneficial. 3 is kind of the Goldilocks zone, maybe between bad and good, and then 4 and 5, that's where you end up having more of the damages.
Generally speaking, and we actually, one of our economists, Tom Cranham, did an analysis and looked at the AR scale, the 1 through 5, and saw that damages associated with each of those scales increased logarithmically. And so the data supports that general framing of 1 and 2 being mostly beneficial, 3 kind of in between, and 4 or 5 potentially hazardous.
Interesting. And yeah, I think that's similar to how either the hurricane or the tornado scale works, which does kind of remind me of the question, are there any kind of similarities or differences between maybe the hurricane scale, which people have been hearing about for decades, which they'd be more familiar with, and your guys' atmospheric river scale?
Yeah, so one of the big differences between the hurricane scale and the AR scale is the hurricane scale is storm dependent, right? So a hurricane has a category, and it can change as it evolves, right? We hear about how a hurricane goes from a Cat 4 and it degrades to 2 to a tropical storm. An atmospheric river actually is different in that it's location dependent. An And so the same atmospheric river at this can have be an AR5 at one point, maybe let's say around the Bay Area, but much farther down the coast where it's not nearly as strong, it could be, say, an AR2. And so because the impacts in these different locations are very different. And so that's one of the major differences, is that it is scale dependent, or location dependent.
Interesting. That ties back to almost your original definition that it's a narrow band of water vapor, and that would be a huge thing for forecasters to remember when you're talking about atmospheric rivers is since it is a narrow band, it might be an incredibly intense storm in one area, and then maybe 100 miles away, it's maybe light to moderate rainfall. So yeah, definitely some nuance in those forecasts would be very important.
Right. And that's actually one of the things that we look at when we look at the verification of how well the forecast did of atmospheric rivers, is the landfall location and how close it was to kind of that maximum intensity of the AR.
Nice. Then, in terms of the forecasting aspect, I know a lot of forecasting, it's kind of in research in progress. I know with some of the wildfire models that we're doing at San Jose State, we're seeing how much more accurate it becomes over time as we're able to collect more data. How, I guess the best way to say it, how good would you say that atmospheric river forecasts are at this point?
So the atmospheric rivers in forecast generally have a longer lead time. So we know that they're coming than, say, precipitation. So that's been documented and shown. And so in thinking about situational awareness and a potential for a storm coming, forecasting atmospheric rivers provide a lot of that information, that those longer lead times. And this is probably true for a lot of different storm types, but we see some variability in the storms, right? Some atmospheric rivers are predictable at longer lead times versus others that are less so. Some of the things that we've seen, so we have a forecast product called the landfall tool, and it shows the probability of atmospheric river conditions. And last winter, when there were so many, some of the longest lead times were up to 10 days for, knowing an atmospheric river was going to hit at a specific latitude. But it was down, I would say on average, it's about 6 days. That we know that something's going to happen, or that an atmospheric river is likely for that location. There's all still getting that, like we talked about, they're relatively narrow and where the impacts will actually hit in that landfall location. And there's other things that are called mesoscale, so smaller that can impact the atmospheric river in terms of duration and how long it lasts. Another big one is what we've seen in California, some of the really high intensity rain that we get are from narrow cold front rain bands. And those can come, at different, sometimes at the end of atmospheric rivers, and it doesn't even have to be that strong. But because those are even more narrow and these smaller scale features, those can be hard to forecast. So it kind of depends on scale and timing, but in terms of the awareness that something's coming, atmospheric river forecast provided a longer lead time than, say, just regular precipitation forecast.
That's interesting. And it sounds like when you're making that scale and trying to forecast whether it's going to be like a 2 or a 5, are the main things you're looking at the intensity, which I guess my question would be, is that based on like how much water vapor is in it? And then, so it'd be intensity on one side and then also duration, because just like with any storm, if it's over you for 10 minutes, maybe not going to drop that much rain, no matter how heavy the rain is. But if it stays over you for 2 days, then that's where you could get some big flooding.
Right. So exactly. The one thing, the intensity is a combination of how much water vapor there is in it, and then also the winds. And so together it's called integrated water vapor transport, or we say IVT, integrated vapor transport. And so it's a combination of these two variables, the winds and the water in the atmosphere.
Oh, that's interesting. And then obviously with more water vapor, you'd be able to get more rainfall, especially up in those coastal mountains. And then that could be where you get your flooding. And I think everyone does associate atmospheric rivers with some flooding, but maybe the ones that aren't as direct, or not direct, but maybe not as close in time period, so people don't associate it as much, would be the impacts it has on drought and wildfire. Would you be able to just touch on how atmospheric rivers impact those two variables?
Sure. So for droughts, an analysis that was done looked at atmospheric rivers as kind of the drought busters. And so
Hmm.
because they are often, not always, our larger storms, they can really help in alleviating or mitigating some of the impacts of drought. What we've seen in California is it's a couple of really big storms that can determine whether it's a wet or dry year. And so those atmospheric rivers can help determine, right, the wet or dry year, and can help alleviate the drought conditions. For wildfires, especially in the fall, right, when we have a wildfire season, we can there are certain thresholds, and it's depending where you are along the coast, after which it's a lot less likely to see a wildfire. And from some analysis that was done, often to reach those thresholds, it's associated with atmospheric rivers.
Yeah, because the more rainfall you get, the more fuel moisture you have, and then more moisture you have in your fuels, the harder it is for fires to start, and then the slower they're going to spread. Yeah, and it is interesting you talk about 2023, because I think that's a perfect example of how atmospheric rivers can be both good and bad, especially up in the Santa Cruz Mountains and the Central Coast. We certainly saw our flooding. But then if you look at the overall state of California, we went from 100% of the state being in drought to 0% of the state being in drought.
Right.
Yeah. So I think you've answered pretty much all the big questions that I had. I guess last one would be, is there anything that you are specifically like excited about in terms of the research, or any kind of big questions that you have right now that you're hoping to answer?
A big effort that the center is doing called atmospheric river reconnaissance. So similar to what they do for hurricanes, have flights that go through and drop instruments into it. We're doing something very similar for atmospheric rivers to improve the forecast. And we've seen over the years how we call it AR recon really does help improve the forecast. And so we're doing that again this season. The other thing that I think is really exciting, we're working closely with the California Department of Water Resources and integrating our forecast and the science into some of their operations in an experimental way right now to see how some more of these more kind of novel approaches can be tested in what they are doing.
Yeah, that's very cool research. So on one hand, you guys are taking planes out to the atmospheric river, dropping basically weather instruments into it, and then you're able to take that data, put it into the forecast model to make it better. And then I think the second thing you just talked about there was, does that kind of tie into, I heard about this last year where they were almost taking some of the forecasts for the atmospheric rivers, and then they were deciding how much water to let out of the reservoirs to try to optimize, obviously, the water supply, but then also optimize not flooding.
Yeah, so the project that you're talking about, and I should have mentioned, is forecast informed reservoir operations, and that's exactly what it is. It's how you can use forecasts to inform, reservoir and when to potentially hold on to water to help mitigate drought or to release water to reduce flood risk.
Yeah, that's very interesting, and I feel like people love to hear kind of. I love to hear the more sciencey aspect side of things, but then I know a lot of other people like to hear how the science can actually be applied to our day-to-day lives. So that's very cool as well.
Yeah, it's great to see the progress that's being made and have some pilot projects. So we're really seeing an impact. So it's great to see those.
Nice, and I can't wait to hear about more of the research that you guys do. And just wanted to thank you again for taking the time to talk with me and help teach me a little more about atmospheric rivers.
Yeah, I'm happy to. And if you ever have any more questions, even if I'm not the one to answer it, I'm happy to connect you with other people on the team.
All right, thank you very much.
Great, thank you.